welcome back to the channel. Today, we are diving into one of the most important components in electronics, the capacitor. What is it? How does it work? And why is it so widely used? Let's find out. A capacitor is a passive element consisting of two conducting plates, separated by an insulator or dielectric designed to store energy in its electric field. Capacitors are one of the most common components in electronics right after resistors. They are everywhere. In radio receivers, in computers, you'll also find them in power systems, communications, and countless other electronic applications. When you connect a voltage source to a capacitor, the source deposits a positive charge on one plate and a negative charge on the other plate. The capacitor stores this charge, and the amount of charge stored is directly proportional to the applied voltage. We can remove the proportionality by introducing a constant C, where C is the constant of proportionality, also known as capacitance of the capacitor. Basically, capacitance is a measure of how much charge it can store per unit voltage. The unit of capacitance is the farad, in the honor of the physicist Michael Faraday. Although the capacitance C of a capacitor is the ratio of the charge Q per plate to the applied voltage V, capacitance doesn't depend on the charge Q or the voltage V. Instead, it depends on the physical properties of the capacitor. For example, in the parallel plate capacitor shown, the capacitance is given by C is equal to A epsilon naught by D, where A is the surface area of each plate and D is the distance between the plates, and epsilon is the permittivity of the dielectric material between the plates. In general, three factors determine the value of the capacitance. 1. The surface area of the plates. 2. The spacing between the plates. And 3. The permittivity of the material. To obtain the current voltage relationship of the capacitor, we take the derivative of both sides of the above equation. And since differentiating charge with respect to time, that is, rate of change of charge, is current, we get the following equation. This relationship holds true for linear capacitors, where capacitance remains constant regardless of the voltage. It is a key concept for understanding capacitors and electrical circuits. Now, let's talk about what happens when you connect a capacitor to a DC voltage source, like a battery. Here is something interesting. If the voltage across the capacitor is not changing with time, in other words, if it is a steady DC voltage, the current through the capacitor is zero. This is because a capacitor acts as an open circuit to DC. So what happens? The capacitor charges up to the voltage of the DC source and just holds the charge. No current flows through the capacitor once it's fully charged. Here is another key point. The voltage across a capacitor must be continuous. It cannot change abruptly. Why, you ask? Because a sudden or a discontinuous change in voltage would require an infinite current. And let's face it, that is physically impossible. Capacitors resist these abrupt voltage changes, which is super important in many electronic circuits. Now, let's see what happens when a capacitor is connected to an AC voltage source. Unlike DC, where the capacitor acts like an open circuit, in the case of AC signals, a capacitor behaves like a short circuit. What does this mean? It means the capacitor allows AC signal to pass through it easily. That's why capacitors are widely used in signal processing and filtering circuits, because they block DC and let AC through. To summarize, for a DC supply, capacitor acts as an open circuit. They charge and hold the voltage. For AC source, the capacitor acts as a short circuit. They allow the AC signal to pass through while blocking the DC. The voltage-current relation of the capacitor can be obtained by integrating both sides of the equation, and upon rearranging, we get the following equation, where V0 is the voltage across the capacitance at the time t0. And we see here that capacitor voltage depends on the past history of the capacitor current. Hence, the capacitor has memory, a property that is often exploited. Let's start with the concept of power delivered to a capacitor. The instantaneous power is given by the following equation. Here, V is the voltage across the capacitor and I is the current through it, and C is the capacitance. This equation highlights that the power depends on how quickly the voltage V changes over time. Now, let's calculate the energy stored in the capacitor. The energy is derived by integrating the power over time. Simplifying the equation, we get energy stored in the capacitor as 1/2 CV square. So this shows that the energy stored depends on the square of the voltage V and the capacitance C. Using the relationship Q is equal to C into V, where Q is the charge on the capacitor, we can rewrite the energy equation in terms of charge, where energy stored in the capacitor is equal to Q squared by 2C. It tells us that the energy stored also depends on the square of the charge Q and is inversely proportional to the capacitance.